In these axioms for points, we also have some useless points in neighbors. For example, in real numbers, for 0, set containing real numbers between -1 and 1, includes 1 and -1, is a neighbors for 0. But what does 1 and -1 brings to our insights? Nothing. Because other than them, all other points as there are enough basic points inside that set. But for 1 and -1, we have missing basic numbers on left for -1 and right for 1. So this set is not just neighbors for 0. It's a neighbors for every elements in that set, except 1 and -1. If we remove that 1 and -1, then we can say this set is neighbors for every numbers in that set. This set is a global neighbor, because of the set itself. Ask to the numbers of the set, who do you guys want me to your neighbor? Then all the numbers in the set will say, for me, because all the numbers in the set has enough numbers needed to define them. Also, this set will allow us to view them independently, since this set doesn't need any extra numbers to define them. By adding more numbers we can view them too. Not just numbers with their neighbors. Technically, a set with this kind, by adding these sets, we can achieve the important thing, that is to view the whole set. Now our goal is to get all those sets of this kind. For that we have to define neighbors for each single element by neighbors axiom, and from those collection we have to collect all those sets of this kind. That's quite a big work. Those collections are our required topology. Let's define those axioms on collection of subsets. The primary motto for each set in that collection is, that set must be a neighbor for each element in that set. The meaning of a neighbor of a point comes from the axioms for neighbors we defined before. There we defined axioms for each and single points, so we have induced that point must belong to every neighbors of that point, but now we can't induce that here, because we are now defining globally. So we have two common subsets for every non-empty set. For every element of those subsets, that subset itself a neighbor. One subset set is quite interesting. You open that set to see what are those elements. Surprisingly, you see nothing there. That's empty set. Every element of this set has their basic points inside the set. You can't disagree with me, that's enough for us here. Another one is whole set. We are going to define topology on a set by believing there exist neighbors defined for each elements. Each neighbors are a subset of this set. So for every point, whole set itself a neighbor. In neighbors for a point, each superset of that neighbor is also a neighbor, because still that set contained enough basic points for that single point. We care only about that single point there. But here we have to care for each and every element of that neighbor. So all superset of a set need not to have this property. For example, if we take this set is a neighbor for each element in that set. But this superset failed to have that property, because 1 and -1 doesn't have enough basic points. We don't have to worry much here. Instead, adding just 1 and -1 in that set, if we add 1 and -1 together their neighbors, then we can sort out that problem. Because 1 and -1 got there enough basic points. We have to be careful here. Those each basic points also must have their basic points in that set. Otherwise that set will lose that property. What we actually did here is union of two sets, where each point of that set, their respective set itself a neighbor for that point. Then the neighbor also has that property. Why just two sets? Suppose if we union arbitrary sets of this property, and that union asks to their points, who do you guys has your enough basic points here? Then all of those points will say, for me, to their respective set. So every point has their enough basic points inside that union. Technically, if we had arbitrary union of sets and pick a point from that union, then that point must belongs to at least one of those sets. That set is a neighbor for that point, so whole union itself a neighbor to that point. Hence for all those points in this union, has their basic points in this union. Similarly, if we take intersection between two sets of this property, there are two possibilities. Intersection may be an empty set, or it may contain elements. If we take any element from that intersection, then that element is presented in both these sets, hence both of these sets are neighbors for that point. It means these two sets belongs to the collection of neighbors of this point. Hence their intersection also belongs to the neighbors' collection. So the intersection may be empty, or if it had an element then their basic points also presented in that intersection. Okay, what about arbitrary intersection? That's tricky one. Suppose you take your infinite intersection. If it's empty, no problem, but if it had an element, that element won't have enough basic points. For example, let's see our autocara Thambi, real numbers. We all know how it's going to be basic points for 0. Let's take the infinite intersection of a collection of neighbors of 0. The neighbor is of the form like this. As n gets bigger, the set shrunk further. That's why their intersection contains 0 only. Suppose if it had other than 0, then that number must belongs to all these sets. It means that number must be larger than -1 by n, and lesser than 1 by n for every positive n. A number lesser than 1 by n, for every positive n, must be 0, or lesser than 0, because, if it's greater than 0, then reciprocal of that number also greater than 0. Let n be a positive number which is greater than this. Then their reciprocal is lesser than actual number. This contradicts our assumption. Similarly, we can say that number must be greater than 0. By these two, there doesn't exist such number. The only number presented in intersection is 0 only. There's no left or right for 0. It lacks their basic points, so this set is not a neighbor for 0. Hence infinite intersection may not satisfy that property, but finite intersection works. By induction it works. So these are the required axioms. We are here collecting all those sets which are global neighbor. That's why our collection must contain both empty and whole set. In empty set we can't point out a point and say this point doesn't have enough basic points. And in whole set, we can say about a point that this point has their basic point outside the whole set, because we are collecting these sets by believing their already neighbors are defined for each point. And also we discussed enough about how arbitrary union and finite intersection of global neighbors carry forward their basic points.